the introduction. So this work is joint work with Dimitri Ostrovsky, Francis Beck, and Alessandro Rudi, and it's on fast rates for regularized empirical risk minimization. So first, let's present the problem. So the setting is the standard statistical learning setting. So we have an input x and output y, and we want to learn a linear predictor theta scalar phi of x, which approximates the output. So here we assume that the feature map phi is infinite dimensional. So this covers so kernel methods. Sorry. So the problem is finding theta star, which is the minimizer of the expected loss, where we give ourselves a loss which compares an output y to a prediction theta scalar phi of x. And so our assumptions are that the model is feasible, so that theta star is in H, that H is a Hilbert space, and that y and phi are bounded. So the classical way of approximating this is solving the regularized empirical risk minimizer. And so this is minimizing the empirical risk with a penalty, a square penalty, with a parameter lambda, which controls overfitting because we're in an infinite dimensional case. So the question is, what is the statistical performance of this estimator as a function of n and lambda? So the existing results for this problem, so the first one is a very general result for slow rates. So if we assume that the loss function is only Lipschitz, so uniformly on y, then we have a simple bias variance trade-off, so with a bias term of order lambda and a variance term of order 1 over lambda n. And so this gives a slow rate, so a 1 over square root of n rate if we choose the regularization parameter to be of order 1 over square root of n. And so we get the excess risk to be of order 1 over square root of n. But what interests us more is so the fast rates that are available for least squares. So in the least squares case, the situation is much richer and we understand it much better. So if we define the covariance operator to be so the expectancy of phi of x, tensor phi of x, which is just like the infinite dimensional version of the covariance matrix. And if we define the two key quantities, the first one being a quantity which characterizes the regularity of theta star and which is equal to lambda squared times the regularized renormalization of theta star, and a notion of dimension, so the effective dimension being the trace of the sigma lambda minus 1 sigma, and this term is bounded by 1 over lambda and is linked to the variance. Then we have a bias variance trade-off, which is more complex, and so we can bound the excess risk by this bias term plus the ratio of the effective dimension over n times sigma squared, where sigma squared basically is like the variance of y. So this is called fast rates because this effective dimension term may not behave as badly as 1 over lambda, and so if it behaves in a more or less constant manner, then we can actually bound the excess risk by something of order 1 over n by choosing a lambda of order 1 over n. So let us just focus on these two key quantities, because when we generalize this to other functions, these quantities will still have the same meaning. So if we decompose the covariance operator so if we take an eigen decomposition of this covariance operator, where the sigma I are the decreasing eigenvalues and the psi are the eigenvectors, and if we decompose theta star on this eigen basis, then the bias term can be, so we can see that this bias term will decrease in a fast way if the coefficients of the decomposition of theta star are reduced, so they're reduced in a fast way compared to the eigenvalues of the covariance matrix. And so we can get an exponent that is faster than just lambda. So, and in the same way, and even easier in a sense, the effective dimension is just linked to the eigenvalue decay of the eigenvalues of the matrix sigma. And so we can see that if these eigenvalues decay polynomially with order alpha, then the effective dimension explodes less fast towards 0 in an order 1 over alpha. So if we input these values in the bound, what we get is so this bound, and we get by optimizing in lambda a rate over n minus gamma, where gamma is between 1/2 and 1, and so in a sense gamma is linked to the bias and the variance and the effective dimension term, and shows that we can actually get faster rates than just 1 over square root of n. So we have a richer situation. And what our contribution is to generalize this richer situation to a broader class of functions, which is self-concordant functions, so generalized self-concordant functions, sorry. So this includes like the square loss, but also different losses like robust regression or cubic losses. And more interestingly, for classification, this includes logistic regression and certain GLMs. So the formal definition of a generalized self-concordant function is that the third derivative is bounded by a constant factor times the second derivative. And I will not go into detail in the proofs, but what this allows us to do is to control the local evolution of the second derivatives and Hessians. And so basically this allows us to have really local rates. So if we want to formulate the fast rates for these generalized self-concordant functions, we have to introduce the Hessian at the optimum and the Fisher information at the optimum. So again, this is purely local. And we introduce the bias and the effective dimension in this way. So the bias term is just basically the same term, except that instead of renormalizing with the covariance matrix, we renormalize with the Hessian at the optimum. And so basically the regularity of theta star would be characterized by its behavior with respect to the eigenvalues of the Hessian at optimum. And the effective dimension here is the renormalization, the trace of the renormalization of the Fisher information by the Hessian. And the rate that we get is exactly of the same form as before. So the excess risk is bounded by this bias term plus the ratio of the effective dimension over n. And so here we get the same thing. We can go up to rate of order 1 over n if the effective dimension is basically constant, which happens for example, for Gaussian kernels. So just to manipulate a bit and to see how this is really a generalization. So if we take the square loss, then the Hessian is just a covariance operator, and the Fisher information is bounded. So it's bounded by sigma squared times the covariance operator, where sigma squared was the sigma square we defined before, and the two main quantities really so there's really an analogy between them. The bias just stays the same, and the effective dimension is bounded by sigma squared times the original effective dimension that we had for least squares, and so we get exactly the same rate. So yeah, thank you for your attention, and if you want to know more about the proof, please come to poster 175. Sorry? I know that the lower bound exists for least squares, and since least square is included in the class, then. Okay, sorry, I don't catch. Wait, I don't catch it. Maybe we should discuss. Yeah, maybe. Yeah. I know it's not the same. It's not disjoint, but it's not. There's not one included in the